Neptune, the most distant planet in the solar system. Discovered through mathematics before it was ever seen, Neptune kept many of its wonders hidden until the James Webb Space Telescope was born, opening a new chapter in our exploration of the universe. Since Voyager 2 first flew past Neptune in 1989, we have witnessed violent winds reaching up to 2,000 kilometers per hour and the mysterious disappearance of the Great Dark Spot. However, recent observations from the James Webb Space Telescope have provided an entirely new perspective, revealing details never seen before about the planet's structure and rings, leaving scientists astonished. Unusual changes in Neptune's atmosphere, from the decline of methane clouds to the unexpected appearance of auroras at high latitudes, have emerged. These discoveries not only challenge our current understanding, but also spark new questions. Let us explore the wonders that the James Webb Space Telescope has revealed. What other secrets might Neptune still hold? Secrets we never even imagined. In August 1989, humanity approached Neptune for the very first time. Voyager 2, the only spacecraft ever to fly past this planet. In the brief moment it swept by, Voyager 2 captured images and data that completely transformed our understanding. At a distance where everything should have been silent because it was so far from the sun, Voyager instead saw a world far more active than anyone had predicted. The strongest winds in the entire solar system tore across its atmosphere, as if Neptune were nurturing a source of energy no one knew existed. The Great Dark Spot, a massive storm the size of Earth, came into view. But only a few years later, when Hubble turned its lens toward Neptune, the Great Dark Spot had vanished without a trace. Voyager 2 stayed at Neptune for only a few hours, and from the moment it disappeared into interplanetary darkness, we could observe the planet only from afar. Hubble, with the sharpest optical eye of its time, continued to monitor this world. As Hubble observed Neptune's storms over the years, a pattern gradually emerged, one that baffled science. These storms did not simply appear and disappear in a predictable cycle. They develop in equatorial regions, drift toward the poles, disappear, and then reappear elsewhere, all in unpredictable cycles. So unpredictable it defied every meteorological model Earth had ever known. And the more we observed, the more we realized that Neptune seemed to operate with its own rhythm. A kind of energy cycle no other planet in the solar system displays so clearly. Neptune emits 2.6 times the energy it receives from the Sun. That is utterly illogical for a frozen world so distant that sunlight takes 4 hours to reach it. What fuels that power? Is it a cooling core or radioactive decay? The unanswered mysteries did not vanish. They simply became clearer. As JWST unveiled a series of discoveries no one had anticipated, when the James Webb Space Telescope turned its enormous mirror toward Neptune. Many scientists believed they were simply preparing to observe a planet already visited by Voyager 2 back in 1989. JWST peeled back each layer of the atmosphere, exposing the faint structure of its rings and revealing disturbances humanity had never seen before. A planet long concealed behind methane and thick optical haze now appeared sharp, vivid, and full of contradictions, as if JWST were allowing us to see Neptune through eyes we never possessed. JWST operates primarily in the near-infrared and mid-infrared ranges, two wavelengths capable of penetrating methane A gas that strongly absorbs visible light and hides most of Neptune's surface in Earth-based observations. What Voyager 2 and Hubble struggled to barely detect, JWST captured with structural clarity. For the first time since 1989, Neptune's ring system appeared, with a level of detail far beyond expectations. Instead of blurry bright arcs, JWST revealed three main rings, along with smaller bright arcs, features that once astonished Voyager 2 due to their discontinuous shapes. In JWST's images, every arc, every dust streak, every edge of every ring emerged with razor sharpness, as if the planet had been placed beneath a microscope. This is not merely a visual improvement, it is a fundamental shift in how we see Neptune. In infrared, dark regions shaped by methane absorption become the backdrop, highlighting bands of material that reflect sunlight. The rings, too faint for Hubble to resolve well, now appear as prominent structures, suggesting that the dynamical interactions around Neptune are far more complex than earlier models assumed. These details carry significant implications. The stable presence of the arcs suggests subtle gravitational influences, possibly from small moons like Galatea, maintaining their strangely asymmetric shapes. However, what JWST discovered goes far beyond dusty rings. Observing Neptune's atmosphere in infrared allowed scientists to track methane cloud cycles over time for the first time. From 2019 to 2023, high-altitude methane clouds declined dramatically on a global scale. This finding, confirmed by research teams using JWST and Keck, marks a major cyclical drop never before recorded. Methane reflects sunlight strongly, so as the clouds decreased, Neptune became dimmer in the infrared spectrum. What is controlling this cloud cycle? The mass disappearance of methane clouds is not an isolated phenomenon. JWST revealed that Neptune's thermal emission distribution changes continuously, indicating that vertical energy transport mechanisms may vary far more intensely than expected. This may be related to fluctuations in ultraviolet radiation from the sun, even though Neptune is so distant that sunlight is greatly weakened. As a result, auroras are not confined to the poles. They spread into unexpected latitudes. This demonstrates that Neptune's magnetic field does not follow the simple rules seen on Earth or Jupiter. If Neptune's atmosphere is already this strange, then what phenomena await us deeper in the convective layers, where the rule-breaking storms originate, may challenge us even more profoundly. As the atmospheric veil gradually opened, it revealed a space filled with movements that were irrational, paradoxical, and governed by rules that even modern planetary science is not certain it can keep up with. Neptune's atmosphere, under JWST's view, was no longer the stable, layered methane clouds described by classical models. It was an open energy field, constantly reorganizing itself, constantly violating the very predictions suggested by decades of physical modeling. One of the first signs of this abnormality lay in the structure of its major storms. For years, Hubble recorded dark storms that appeared and vanished on perplexing cycles. But JWST allowed us to look directly into the atmospheric layers supporting them. And immediately, a paradox emerged. Neptune did not simply have storm cores. It had secondary bright regions recorded with high detail, often appearing next to the large vortices. The companion bright spot, a bright, stable structure existing alongside the main storm, has no equivalent in the atmospheres of Jupiter or Saturn. JWST showed that these bright spots strongly reflect infrared light, suggesting the presence of cold air columns rising from lower layers, held in place by an asymmetrical wind system. Looking more closely, the companion bright spot is not a random accessory. It operates almost in sync with the main storm, refusing to dissipate even as the storm shifts position with the zonal winds. This raises the possibility that on Neptune, storms are not solitary structures but multi-core systems, a form of atmospheric dynamics Earth has never seen. Why would a planet with an average surface temperature near 220 degrees Celsius generate something this complex? What within Neptune's deeper layers produces these bright, cold columns operating far outside conventional rules? Long-term measurements also indicate that Neptune's atmosphere is undergoing temperature variations far greater than we once assumed. Over more than 20 years, data from Keck and VLT recorded an approximate 8 degrees Celsius drop in the troposphere. A significant change for a giant planet. But even more shocking is that JWST revealed Neptune's south pole warming by about 11 degrees Celsius, creating a geophysical paradox. The entire planet cooled, except for a warming south pole. This may reflect changes in the vertical circulation of the atmosphere or increased sunlight absorption through cloud gaps. And then JWST recorded the appearance of the trihydrogen cation, a molecular ion that forms only in strongly ionized environments. The trihydrogen cation had previously been detected on Jupiter and Saturn in auroral regions, but its broader distribution on Neptune reveals that this atmosphere is experiencing ionization processes beyond expectations. The trihydrogen cation forms when hydrogen atoms lose electrons, something that typically occurs when high-energy particles from the solar wind or the planet's own magnetic field collide forcefully. Its presence indicates that Neptune's upper atmosphere is a space shaped by invisible energy streams, constantly sculpting its chemical composition. But the deeper we go, the stranger Neptune's chemistry becomes. JWST detected unusually high amounts of ethylene and acetylene, two light hydrocarbons typically produced by photochemical methane reactions. On Neptune, their concentrations vary by region, are not uniform with altitude, and do not align with standard photochemical models. Some atmospheric regions show older chemical signatures, where molecules have undergone multiple radiation cycles, while others appear younger, as if Neptune is running a continuous chemical conveyor belt, pushing material up and down through previously unknown cycles. The existence of these chemical layers suggests that Neptune is an extreme chemical laboratory, where methane is not simply broken apart by sunlight, but is also shaped by internal heat, a strongly tilted magnetic field, and violent vertical mixing between atmospheric layers. This may create boundary layers where gases of different densities and temperatures slide past one another, enabling storms to form rapidly and dissipate rapidly. The more we explore, the more we realize that Neptune is not a planet of stillness. It is a world of ceaseless motion, not chaotic motion without meaning, but motion guided by new rules. Rules humanity is only beginning to glimpse. Amid the cold darkness at the edge of the solar system, where temperatures can drop below 1,230 degrees Celsius and sunlight is 900 times weaker than on Earth, lies a world coated in bright nitrogen ice that gleams like metallic glass. Triton, Neptune's largest moon. All the data humanity has collected so far leads to an unofficial but increasingly undeniable conclusion: Triton was not born to be a moon. The clearest confirmation of this lies in Triton's retrograde orbit. It moves around Neptune in the opposite direction of Neptune's rotation. No other large moon in the solar system shares this characteristic except Triton. In addition, its orbit is tilted nearly 157 degrees Celsius relative to Neptune's equatorial plane. This is the signature of a gravitationally captured object, not one formed alongside its parent planet. Triton's original orbit was likely chaotic enough to disrupt and destroy many of Neptune's early moons. This explains why the Neptunian moon system today appears distorted, with smaller moons like Proteus and Nereid following eccentric and unstable paths. Its strangeness goes far beyond its origin. Triton is also geologically unusual. When Voyager 2 flew past Triton in 1989, it captured nitrogen plumes erupting 8 kilometers high, a phenomenon possible only if internal heat exists beneath the nitrogen ice shell. These plumes didn't just release nitrogen into the atmosphere. They dragged dark dust upward, creating long black streaks stretching hundreds of kilometers across the surface. No other moon in such frigid conditions possesses active cryovolcanoes. In fact, Triton is the coldest object ever directly measured, around 235 degrees Celsius, yet it somehow maintains dynamic, continually refreshed nitrogen ice. This can only occur if the subsurface is warm, not from the sun, but from tidal forces. Neptune, with a mass 17 times that of Earth, exerts tidal forces strong enough to compress and expand Triton rhythmically throughout its orbit. This flexing generates internal friction that heats the deeper ice layers. And this very heat drives Triton's cryovolcanic engine, keeping it alive and active even though sunlight barely reaches its surface. JWST is the first instrument since Voyager capable of observing Triton with detailed infrared sensitivity. And its data reinforces an important fact: Triton is still active. The reflections of water ice and nitrogen ice behave in ways that can only occur when these layers are constantly renewed. This means Triton's cryovolcanoes are not relics of the past. They are ongoing today. And to fully understand this connection, we must look deeper into Neptune itself, into the churning layers of hot and cold gases, into the mysterious energy source that allows Neptune to radiate twice the energy it receives, and into the 2 km/h winds rising from its depths. What makes Neptune extraordinary is not its distance or its cold, but the fact that it contains physical mechanisms that challenge everything humanity currently understands about ice giant planets. The starting point of all its mysteries is internal energy. Measurements from Voyager 2 in 1989, later confirmed through infrared observations from Hubble and Keck, show that Neptune emits twice the energy it receives from the Sun. This number is not an error. It has been measured consistently for decades. One scientific hypothesis involves the stratification of hydrogen, helium, water, methane, and ammonia within Neptune's interior. Under immense pressure, these molecules may separate into layers and release heat, similar to crystallization processes that release energy, but no direct evidence yet confirms this. Another hypothesis involves collisions and friction between supercritical material layers that are neither solid nor liquid, existing in a special state under hundreds of gigapascals of pressure. These layers may generate unpredictable thermal flows, allowing energy to escape unevenly with depth. And within this extreme pressure temperature environment, scientists believe a bizarre phenomenon may be occurring: diamond rain. Laboratory experiments at Slake simulating Neptune's conditions have observed methane breaking apart, carbon crystallizing into nanodiamonds, and falling downward like rain. But if Neptune's energy is a mystery, its winds are another paradox. With speeds exceeding 2.1 km/h, they are the strongest in the solar system. Not only are they powerful, but they also shift with altitude, something JWST has recorded through variations in color and temperature within the troposphere. On Earth or Jupiter, winds typically increase with altitude to a limit and then weaken. But on Neptune, wind speeds can suddenly increase in certain layers, then drop sharply in the next astonishingly abrupt. What mechanism could produce this? Part of it may come from Neptune's rapid rotation. This fast rotation generates strong Coriolis forces that fragment the atmosphere into axial wind bands. But rotation alone cannot explain the extreme vertical variability. This has led researchers to believe that Neptune's winds are not governed solely by solar radiation or internal heat, but by the interaction between both energy sources. JWST data also shows that Neptune has inverted thermal gradients in many atmospheric layers in some areas. Temperatures increase with altitude. All of this excess energy, multi-layered swirling winds, deep cyclical structures, is not merely the expression of a strange planet. Neptune may be the key to deciphering the thousands of Neptune-like exoplanets that JWST has discovered across the galaxy. The sharp infrared images from James Webb erase the old idea of Neptune as a quiet, frozen world. Discoveries of unexpected changes in its atmosphere, cooling regions that do not follow any known cycle, and energy signatures never recorded before have forced the scientific community to reconsider the entire model of how this distant planet operates. Neptune is no longer a defined object, but a complex dynamical system governed by physical processes we cannot yet fully explain. Are the changes Webb is observing signs of a cosmic cycle humanity has never had the chance to witness? As JWST continues to probe deeper into the data layers, Neptune has moved beyond the role of the farthest planet in textbooks. It has become powerful evidence that even at a distance of 4.5 billion kilometers, the universe still holds silent, hidden mechanisms at work. Every advance this telescope makes not only reveals a clearer view of a once obscured world, but also expands the boundaries of our understanding of the formation and dynamics of the entire solar system. The journey to explore Neptune has only just begun. And James Webb has proven that the greatest surprises in science always wait where we least expect.
Wide-angle shot of Neptune, revealing the mass disappearance of methane clouds.
The clouds shift and interact in unpredictable ways.
Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.